All right, you guys. So whenever we've talked about salts before, like last year, we looked at solubility rules, right? Like you were trying to decide, is this salt going to be aqueous in solution or is it going to precipitate out as a solid? And the way that you determine that was just by reading the solubility rules or memorizing the solubility rules and saying, okay, this salt is soluble or this salt is insoluble. Well, like it's more complicated than that, okay? Even these salts that we call insoluble, like a little bit of them does dissolve. Not very much, but like a little bit. And salts that we say are really soluble, like it's not like you can dissolve as much of it as you want, like all of it will always dissolve. There are degrees of solubility, okay? And some salts are more soluble than others. And so in order to understand what's going on, we have to look at salt solubility in terms of equilibrium, okay? So the easiest way to understand this is to consider a saturated solution. If a solution is saturated, and remember, the temperature your solution is at is going to also determine how much salt can dissolve, right? So if I say this is saturated at 25 degrees Celsius, there's going to be a different saturation point at higher or lower temperatures, right? You can dissolve more of it when it's hotter and less of it when it's colder. Okay, so like let's say we have a saturated solution. That means that you've got like your maximum amount of dissolved ions. We'll consider only ionic salts here for this conversation. So you've got as many ions as possible. So like let's pretend in this diagram that this is saturated. That means that this volume of water has as many dissolved lead and chloride ions as possible. And you'll notice that I showed 2 chlorides for every 1 lead because the formula for the salt is PbCl2. Down here at the bottom, this is undissolved PbCl2 solid, okay? So as much of it could dissolve did dissolve, and those ions are floating around in solution. And then the rest of it that could not dissolve is sitting down here on the bottom of the beaker. You might think that this is like a static situation, but you should know better by now in chemistry that all of these processes are dynamic. Like these ions are floating around and crashing into each other and making contact with the solid down here at the bottom. So what will happen is because of the just internal kinetic energy that this system has, there are going to be collisions between these ions that cause them to precipitate out as a solid. But as soon as you have anything precipitating out as a solid, that leaves more room in the solution for other ions to dissolve into solution, right? So you've got this dynamic equilibrium here of solid particles ionizing in solution, and then those ions crashing back together and coming back out as a solid. Okay, so when we have a saturated solution, yes, you have as much dissolved solute as possible, but you also have what we call dynamic equilibrium. And like any equilibrium, like Kc, Kp, Keq, Ka, Kb, Kw, all of these K things, right, are the products raised to their coefficients over the reactants raised to theirs. So like I could write a Ksp expression for this salt. We call it Ksp. I'll tell you what it stands for in a second. It has to do with solubility. The Ksp would be the concentrations of your products, so the Pb2 plus ions and the Cl minus ions, don't forget, raised to their coefficients. We haven't done that in a while, right? Because all of these acid-base ones we've been doing, we're all like 1-to-1s. Over your reactants. But notice I'm not drawing it over my reactant, and that's because my reactant is a solid, right? Remember, we only include in our equilibrium expressions substances that are aqueous or gas, okay? We don't include this solid because it has a concentration of 1, like it's pure. So we don't include pure substances in our equilibrium expressions because these are affected by, well, an equilibrium expression is really related to the rate of the forward and the reverse reaction, and rates are only affected by things of differing concentrations or pressures. So having more solid here in the bottom of the beaker is not going to affect the equilibrium position of this salt. So this right here, you guys, this is just this is called my solubility product constant, KSP. It's just another version of KEQ. It's a KEQ for a salt. Products raised to their exponents over reactants raised to theirs. Just like all of our other K values that we've talked about, if you have a big K value, that means your equilibrium really lies to the right, right? So if you have a KSP much greater than 1, that is a very soluble salt. And if you have small KSP values, K is less than 1, you have a relatively insoluble salt. So big K's, soluble. Small K's, insoluble. And of course, any degree in between. Questions so far?
Yeah, if you flipped that reaction, now big K's would be relatively insoluble, right?
No. So because the state's, good question, Matthew, because this, if I flipped this reaction, now, right? So if I flipped it, Pb2 plus and 2Cl minus, making PbCl2 solid, I would have to do 1 over. Do you know what I mean? I would, like, whatever the K is for this reaction, I would do 1 over it for its reverse reaction. You know what I mean? And so, you know, if for whatever reason you get a value for this, right? And so you're going to get a very, yes, you're going to get a very big K value. You have to like look at it and say, okay, well, if you have a big K value lying to the right, that's where it's a solid. Do you know what I mean? So we only write these reactions, Matthew, this way. We don't really flip these reactions because when we're talking about how soluble is something, we're talking about it going from its solid state to its aqueous state. So I see what you're saying, which is like, if I took the inverse of this, yeah, now all of a sudden I'm going to get a big number. Yeah, you're going to get a big number, which is pointing you to the right, towards where it's a solid. So we just don't ever write it that way. Does that make sense?
Yeah.
Okay, cool. Sorry, I know you have your video on, but I hit all of you guys, so you don't show up in the recording. So if you guys are nodding at me, I have no idea. Okay. Let's talk about what the K value is for this particular salt. Okay, so for this lead chloride salt, you can find these KSP values in Appendix D, which is where you can find KAs and KBs. And you'll notice that the only time you have a K value is for a relatively insoluble salt. Like they're not going to give you K values for things like sodium chloride, which are super duper soluble, right? Like really big Ks, we don't record them. We just say, the equilibrium lies to the right. They all dissolve completely. Same thing with like strong acids and strong bases. We don't even report the Ka or the Kb value. We just say, hey, it goes all the way to the right. So same thing for salts. I picked a salt that's like moderately soluble. Lead chloride, 1.7 times 10 to the negative fifth. And these are unitless, just like Kas and Kbs are, and KEQs, all of the K values, all right? So a very common type of question for these salt solubilities would be, okay, if you've got this salt and you have this KSP value, one question that you might be asked is, what is the concentration of the lead plus at equilibrium? And I don't know why I drew 2 question marks, that looks stupid. And what is the concentration of the Cl minus at equilibrium? And so whenever we're being asked about things at equilibrium, like how much of these ions are we going to have dissolved in solution, you need to do a Rice table, just like we've been doing. Okay, so really there's nothing new here. This is the reaction that we're going to Rice table. Rice table this reaction, you guys. C, E. All right, now we don't include the solid. We start off with none of this and none of that. As this salt goes to dissolve, we're going to gain some of this. And you got to pay attention to your coefficients. I know we haven't done coefficients in a while. We're going to gain 2x of this. Okay, so at equilibrium, I'm going to have X amount of lead, and I'm going to have 2 times as much chloride because of the way that this salt is formed and dissolves. So now I can just plug my variables into my Ksp expression. So I've got X times 2x, and here everybody always forgets, don't forget to square it. Okay, there's a squared right there, equals 1.7 times 10 to the negative 5th. All right, grab your calculators. So 2x squared is going to be 4x squared times x. So we are at 4x cubed, 1.7 times 10 to the negative 5th. And you know, depending on how fancy your calculator is, you probably have a cube root button. I'm using I don't have my fancy calculator with me. You can always raise something to the 1/3 to get a cube root. So I'm going to divide by 4 and then take the cube root of it. And for x, I got 0.0162. Now this is a concentration, right? This is x right here. This is how much lead I'm going to have at equilibrium. So I'm going to give that a molarity. This is how much of the lead 2+ I'm going to have at equilibrium. And then to figure out how much chloride I'm going to have at equilibrium, I need to take that number and I need to multiply it by 2, because you get twice as much chloride as lead. So my concentration of my chloride is going to be 0.0324 molar Cl minus. And those are the concentrations that you're going to have at equilibrium. Another very common type of question, and I'll just add on to this question. Another thing that they would ask is, what is the molar solubility of this salt? I don't know why I keep putting question marks at the front and not the back of my statements. Okay, so what is the molar solubility of this salt? When it asks the question in this way, you guys, it's asking about how much of this, like what molarity of the thing as a whole can dissolve, okay? And so all you have to do is just pay attention to the stoichiometry, okay? Molar solubility is always referring to the salt as a whole before it has split up. Do you guys see how it has a 1-to-1 mole ratio with the lead 2+? Right? For every 1 mole of this, you get 1 mole of lead 2+. So if I was reporting the molar solubility of this salt, I would say it was the same as the lead 2+, 0.0162 molar PbCl2. That is the molar solubility of the salt. Questions on that?
Yeah, I think I understand what you're saying. The PbCl2 is, you're just saying if you have enough of that to reach, like it doesn't matter as long as it's just more than the maximum solubility.
Yeah, it's the saturation point. Like this is,
yeah, that's
exactly. Yep, exactly. Very good. Okay. Let's do another practice problem with this. Let's say I have the salt, silver chromate. All right, so first thing I'd like you guys to do, so another example problem, Ag2CrO4. This is silver chromate. Chromate is a polyatomic ion. Okay, remember your polyatomic ions stay together. as they dissolve. So first things first, please write for me what this is going to break up into. Pay attention to your subscripts here. They become coefficients and your charges. And also write for me the Ksp expression, please. Okay, so dissociate your salt into its ions, and then tell me what that equilibrium expression should look like.
Mrs. Rivera,
Yeah.
so do we only do this for like not very soluble salts?
Yes, exactly. If I told you that a salt was super soluble, or like for example, alkali metal salts always super soluble, ammonia, ammonium salts always super soluble, nitrates, they have huge K values, and so we don't even bother with the equilibrium. We just say, hey, if you've got this much of the salt, that's how much of the ions you're going to get. You know, it's always like a complete dissociation, equilibrium wise, all the way to the right. Yeah, so if you go to look up a Ksp value for something in the back of the book, you might not find it because that salt is really soluble.
Okay, thank you.
Yeah. In fact, like you're really not even going to see values much bigger than 10 to the negative third, fourth, fifth. Like, in fact, if you go look at Appendix D, you're going to see some really, really insoluble salts, like 10 to the negative 27th, 10 to the negative 11th. Yeah, it's not a super useful thing for us to look at unless we're talking about something that's just not very soluble. All right, so this one, we're going to get 2 silver ions for every 1 chromate ion. This must have a 2 minus charge. Remember, silver is always a 1 plus, so this must be a 2 minus if there needed to be 2 of them. And the Ksp expression is your products raised to their exponents, or coefficients, sorry. Coefficients become exponents, and the chromate. Another type of problem that you're going to see is asking you, what is the Ksp for this salt if it has a molar solubility of 1. A molar solubility of 6.5 times 10 to the negative 5th molar. Okay, so we're looking for Ksp, and it gives us molar solubility. Remember, molar solubility is referring to this thing as a whole, right? So like the maximum amount of this as a whole in order to dissolve at 25 degrees Celsius or whatever is this molarity, okay? So what I like to do for these rice tables here, RICE, remember, we're not going to include this, is I look for the ion that it has like a 1-to-1 proportion with, right? Like this is just stoich here. For every one of these, I get 1 chromate at equilibrium. All right, so I'm going to start off with none of this and none of this. But if this is the solubility of the salt as a whole, this is also going to be equal to the concentration of the chromate, because it's a 1-to-1 mole ratio with it. Okay, so my chromate concentration at equilibrium is going to be 6.5 times 10 to the negative 5th. So down here in the equilibrium portion of my rice table, I can put that 6.5 times 10 to the negative fifth. So that must mean that the change was plus 6.5 times 10 to the negative fifth. Maybe it's a little bit overboard to do this. So now we need to figure out, okay, well, how much silver are we going to have, right? For every 1 chromate, we're getting 2 dissolved silver ions. So I need to take this number and multiply it by 2 for my change with the silver. So 6.5 the negative fifth times 2. So I'm going to get plus 0.00013 of my silver. I guess I should have stayed in scientific notation, whatever. 0.00013. All right, so does everybody see what I did right there? Your molar solubility is referring to the salt as a whole. Pay attention to your coefficients to figure out, okay, well, what does that mean about the solubility of each of the ions? Do your rice table. Once you know your molarities of your ions at equilibrium, then you can take these values and just plug and chug into your Ksp expression to solve for the Ksp of this salt. So the Ksp is going to be equal to the silver concentration, 0.00013. Don't forget to square it, times the chromate concentration, 6.5 times 10 to the negative fifth. I got 1.1 times 10 to the negative 12th. Not a very soluble salt. All right, I'm gonna pause recording for a minute. Okay, so the last thing I want to talk about with regard to salt solubility is that there are different things that can affect how soluble a salt is. Okay, so we need to talk about some factors affecting solubility. Like we can make things more or less soluble. So obviously there are a couple of things that we already know that matter, right? So obviously temperature matters. Temperature affects solubility. Right? If you increase the temperature, you can increase the amount of solute that can dissolve. So we already know about that one. We also already know, even though maybe we haven't applied it to this situation yet, is the common ion effect. We talked about this with strong and weak, with weak acids and weak bases, the common ion effect. In the presence of a common ion, less salt will dissolve. Okay, so like for example, with that PbCl2 that we were talking about before, let's rewrite that equilibrium just so we can see it happen here. Pb2 plus and 2 chloride ions. Okay. We said that this was saturated at a certain, molar solubility. I don't remember what it was, but whatever. We said it was saturated, and a certain amount of Pb2 plus can dissolve and a certain amount of Cl minus can dissolve. But if you tried to dissolve this salt, this PbCl2, in a solution that already contained a bunch of chloride, right? So like, let's say also in here was already a super soluble salt, like NaCl. Notice the arrow goes one way, right? Na plus and Cl minus. Alkali metal salts, very soluble, okay? If there's a bunch of sodium chloride in here, you're gonna have a bunch of chloride already in solution taking up space. So Le Chatelier's principle tells us that if we increase the chloride ion concentration from some other source, that's going to shift this equilibrium to the left. There's going to be less room for this salt to dissolve, and you're going to end up getting some of these lead chlorides precipitating out. That's what I mean by the presence of a common ion. Okay. And lastly, I need an example here for this one. I don't remember what I wanted to do. Ooh, yes. Okay. Lastly is pH. pH can affect solubility of certain salts. So like not all salts, right? Like all salts will be affected by temperature. All salts will be affected by a common ion. pH only affects certain salts depending on what they're composed of. And you'll see what I mean here when we do a little example. All right, so let's do a pH example. Let's say the salt that I'm talking about is a hydroxide, like MgOH2. Mg2 plus and 2OH minus. Okay. If this is saturated, it's got, maximum amount of magnesium, maximum amount of hydroxide. It's happy. It's going back and forth at whatever its, Ksp value is. I don't know. What's the Ksp for this salt? I think it's pretty small. 1.8 times 10 to the negative 11th. Okay, so like, yeah, not a ton of these ions. If I were to try to dissolve this salt in a basic solution, okay, so if I try to dissolve in basic solution, so like a pH greater than 7, that means that I'm trying to dissolve this salt in a solution that already has lots of OH minus. That is going to make this salt less soluble. It's like the same thing as the common ion effect, right? But we're just talking about the common ion being hydroxide, okay? So this particular salt will become less soluble in basic solution. But your next question should be, well, like what would happen if it was in acidic solution? If we try to dissolve this same salt in acidic solution, like a pH less than 7, you're trying to dissolve this in a solution that has lots of H plus. And that might not be super obvious about what's going on here, because like you don't see any H plus here in this equilibrium expression. So you're like, what effect is that going to have? Well, these H pluses, they love OH minuses, right? H plus grabs onto OH minus to make water, H2O. So if that's the case, I'm going to be removing these OH minuses from solution because they're going to be reacting with the H pluses in my acid to make water. And that's going to shift the equilibrium to the right. Okay. And it becomes more soluble in acidic solution. So for all of these KSPs that are given in the back of the book, these are given at 25 degrees Celsius and neutral solution. Any changes to temperature or any changes to the pH is going to do the whole Le Chatelier principle thing and affect the solubility. Is this reaction going to shift left, which would mean precipitating out as a solid, less soluble? Or is it going to react with one of the products and reduce their concentration and shift it to the right and make it more soluble? I want to do one more example of pH. Let's do PbF2. PbF2, solid. So we're going to get some Pb2 plus. And we're going to get some F minus. I don't know what the KSP is. It doesn't matter. The point is that this is that equilibrium. You've got some of these ions, not a ton, and you've got some of this solid. Let's look at this particular salt and see what happens in acidic solution. Like a pH, again, less than 7, which means we're talking about lots of H plus. This one is really unclear about what kind of an effect this is going to have. Okay, you got to like dig deep in your chemistry here to try to figure out how is this H plus going to affect this equilibrium. What you need to recognize, so look at H plus, like positive charge, not going to interact with something with positive charge, right? But could something with positive charge react with something with negative charge? It could. In fact, we know that H plus F minus, this is like a kind of strong conjugate base. Like it will, in fact, make some HF, which is a weak acid, okay? So if what you have here is a conjugate base of a weak acid, it'll react with this H plus just like the OH minus did, right? So if you have one of these conjugate bases that's like reactive enough to react with the H plus, you're going to lose concentration of F minus because it's going to do this reaction over here. And so this is going to shift to the right again, just like it did up here. Up here, it was obvious because you're like, oh yeah, H plus OH minus makes water. But it's also possible that you can get something to be more soluble in acidic solution, not because you're making water, but because you're making weak acid. All right, so this is another example of more soluble in acidic solution. Now, the AP exam probably, like, how would they ask this question? They would probably do something along the lines of like, tell me why this salt is more soluble in acidic solution. So you wouldn't necessarily need to be able to predict that it was going to be more or less soluble, but if they tell you that it's more or less soluble, you want to be able to explain why. Okay, so there's a question. Will it make the solution more acidic? So like how would, let's say you try to dissolve this particular salt in a solution that's already at like pH 6 or something. You're gonna end up absorbing some of these extra H pluses that are already there, and those are gonna become HF. So it'll become less acidic over time as this salt dissolves. So the question was, you guys, like, all right, so like, let's say you have this solution, right? And in this solution is just like, I don't know, it's like it's like a pH of 6 or something, right? Because you have a little bit of like extra H pluses in there. And then you go to dissolve this salt in it, PbF2, right? The question was, what's going to happen to the pH of this slightly acidic solution as this salt dissolves? It's like a really, really smart question. What's going to happen is, because these extra H pluses that are just floating around will react with whatever F minus happens to be available based on the solubility of the salt, these are going to become molecular HF. Like, this is a weak acid, which doesn't dissociate very much. So I think it's going to actually absorb some of this extra H plus, and we're going to actually see this pH go up a little bit when that salt dissolves. That's what I think is going to happen, but they're never going to ask you that. That's like 2 steps beyond what we need to be talking about. It's a really good question, though. Okay. So, you know, I think that's all I want to talk about. Isn't that nice? Look at it. I didn't even take up the whole hour. All right, I'm going to stop recording. There's a problem set to do. So